we'll discuss an application of trigonometry instead of trigonometry. And it's called polar coordinates. You'll see these, they're kind of like radar coordinates. You know, when you see a radar go around, what you're interested in is the distance from a point called the pole that's at the center of the radar, and the direction you are from that. And here's other applications. By the way, this is coming out of a free online resource that you can get, I'll recommend it to you, called LibreTexts. If you just Google LibreTexts polar coordinates, you can get these things to look at yourself. I think this is a nice supplement to the textbook, so I'll go out of here, and the textbook is very similar also. So here's an example of boat. You might be interested in the direction of the wind, where it's coming from, and what its strength is. Polar coordinates work like this. If you have a point in the plane, like right here, instead of saying, well, drop a perpendicular and get its x-coordinate, drop a perpendicular and get its y-coordinate, and get an xy pair to identify the point, you can instead identify it by how far it is from what we usually call the origin. In polar coordinates, it's called the pole. How far it is from the pole and what angle it's at, right? So it's trigonometry coming in here for the angle. And if we go at an angle of pi over 4 and 2 units out, we get this point right here. Those rectangular coordinates, if you figure the triangle, are square root 2 is 1.4 by 1.4 roughly. So polar coordinates are an alternative identification method for points when it's more convenient to say how far away is it and what angle is it at. Here's another one. Suppose I want to plot the point with polar coordinates. The first one is called r and the second one is called theta. R for the distance and theta for the angle. If I want to plot the point 3 pi over 2, what you usually do is you turn through the angle theta first and then you go out the distance r. So I'll turn through pi over 2 radians, it's a 90-degree angle, and then go up 3 units, and it's right there. The polar coordinates for the point with rectangular or Cartesian coordinates 0, 3 are 3 pi over 2. The distance you went out followed by the angle you turned through to get there. Suppose I want to plot this point, minus 2 pi over 6. Didn't we say that r was the distance out? Well, it can be, but we make one additional exception just for generality of applications. It turns out to be convenient to allow r to be negative and the angle to be the opposite direction. So I can go to points with negative r values by turning to this angle and then backing up whatever number of units this is. So I go backwards 2 units. Let's plot the point minus 2 pi over 6. I'm going to turn through an angle of pi over 6. That's right 30 degrees, so it's 1/3 of a right angle. It's about here. And then I'm going to back up 2 units, 1, 2, since r is negative 2. And the point with coordinates minus 2 pi over 6, polar coordinates, is actually this point right here. Turn through pi over 6, go negative 2 units. Now, how do we convert between rectangular and polar coordinates? We can see these are kind of convenient in things like which direction is the wind blowing, or what direction is it on the radar, or something like that. If we're given polar coordinates and rectangular coordinates, so rectangular or Cartesian coordinates x, y, and polar coordinates r, theta, describing the same point, then this is the picture. X and y are the rectangular motion you make. R is this distance away or minus thereof, and if you're taking r positive, then theta is this angle. What you find out is that from this triangle, x, this side, has to be r cosine theta, right? What always happens is when you have a hypotenuse r and an angle theta, one side is always r cosine theta and the other side is r sine theta. These is extensively in lots of classes with physical applications. The reason being that if this over this is the cosine of theta, right, adjacent over hypotenuse, so we write, hope you can see this on the camera, x over r equals equal to r cosine theta. So this is r cosine theta, and similarly, since y over r is sine theta, y must be equal to r sine theta. So that tells us that the conversion from r and theta polar coordinates to rectangular coordinates is to set x equal to r cosine theta, y equal to r sine theta. That's converting in one direction. Given r and theta, I can find x and y. I want to also be able to go the other direction, right? Well, what's the other direction? Let's see. I guess they're going to do it in a minute. Lost track of where that is. Here's converting from polar coordinates 3 pi over 2 to rectangular coordinates. You just say x is r cosine theta is r cosine pi over 2 is 0. Y is r sine theta is 3 sine pi over 2 is 3. So we get the point 0, 3 as in the previous example. So 0, 3 is the same, rectangular coordinates is the same point as 3 pi over 2 polar coordinates. Alright, now, let's see. Here's another one. Suppose I want to write the polar coordinates minus 1, 2 pi over 3 as rectangular coordinates. No longer an axis. You can just click on it here. And it gives you the thing after you do it yourself. So it's kind of fun under these problem sets. But I take, for x, I take r cosine theta. Now I have a negative r, but it turns out the formula still holds. Minus 1 times cosine 2 pi over 3. You can kind of picture on a unit circle and say, oh, this is minus a half. Minus 1 times cosine of this is minus a half gives plus a half. And if I take r times sine of this angle, so minus 1 times sine of 2 pi over 3, we call the square root of 3 over 2. Just do it on the unit circle. So minus 1 times square root of 3 over 2 is minus square root of 3 over 2. It's the same formula when r is negative. Now suppose I want to go the other way. Again, we look at this triangle and you look at by the Pythagorean theorem, x squared plus y squared equals r squared. And so we have this equation, r squared is x squared plus y squared. You say, why don't we write r equals square root of x squared plus y squared? We can if we want r to be positive, but we're also going to allow r to be negative, so we'll leave it like this, and you can solve this and choose r either positive or negative, whichever one you want. Now also you notice that the tangent of this angle is y over x. That tells us how to find theta, except that there's an ambiguity. I could take theta equal to the arctangent y over x, and I get this angle here, or I could add 2 pi to it and go in the same direction. It would still identify this point. Or I could add 4 pi or 6 pi, or I could subtract 2 pi. There's actually an infinite number of polar coordinates for any coordinate here. It's not like xy coordinates where there's only one xy thing to identify each coordinate, because you drop the perpendicular, that's it. x0, y0 are the coordinates. In polar coordinates, you can add any pole rotation to theta, any mole of 2 pi in radians, and it will identify the same point. So each pair r theta identifies a unique point, but there's actually an infinite number of pairs r theta to identify any particular point. But we have these two equations. R squared is x squared plus y squared. Tangent theta equals y over x to convert rectangular to polar coordinates. And then there's a little more ambiguity, because I can choose r positive or negative, or 0 if x squared plus y squared is 0. And theta can be the arctangent if you're in quadrants 1 or 4 and r is positive. Or it can be the arctangent plus pi, right? Because the angle whose tangent is y over x is actually not arctangent when you're in quadrants 2 or 3, it's arctangent plus pi. We'll get to that here. But recall that from when we calculated angles before. If we wanted to solve all angles whose tangent was a given number, there were two solutions, the arctangent and the arctangent plus pi. The arctangent always came out in one of these two quadrants, the arctangent plus pi came out in these. It follows that when you're solving this equation, you take the arctangent and then you consider which quadrant to decide whether to add pi or not. And then on all those you can add any multiple of 2 pi and it's the same direction. So let's try this on this one. Suppose I want to find the point whose rectangular coordinates are 3, 3 in polar coordinates. Well, suppose I choose r equals square root x squared plus y squared so that r is positive. Then r is square root 3 squared plus 3 squared is the square root of 18, reduces to 3 square root 2. There's r for this point whose coordinates are 3, 3. Now what's theta? Tangent theta is y over x. 3 over 3 is 1. I know an angle whose tangent is 1. It's the arctangent. It's pi over 4. So one choice for theta is pi over 4, and I could say the coordinates to this point are r equals 3 square root 2, and theta equals pi over 4. And here's the picture. I can turn through pi over 4 and go out 3 over square root 2 units and get to the point whose rectangular coordinates will be 3, 3. Or I could just go over 3 and up 3 and get to that point. That being said, there are other ways to do this. I could, for instance, take r equal minus square root 3 over 2, going the opposite, going r negative, and go the opposite direction. If I add pi to this angle pi over 4, then I'm going the opposite direction, 5 pi over 4. And if in the direction 5 pi over 4, I back up square root 3 over 2 units, I will get to the same point. So every point in the plane, other than the origin, which has r equals 0 and theta can be any angle, has a pair of coordinates, one with r negative and one with r positive, that differ in the angle theta by pi. And then also you can add any multiple of 2 pi to either angle and identify those coordinates. So there's an infinite number of ways to pick polar coordinates with r positive and the angle to the point, and an infinite number of ways to polar coordinates to take r negative and theta opposite the direction of the point. So here's one with r negative. If you go to 5 pi over 4 and back up 3 square root 2 units. Here's one with r positive. You go in a different angle than we had up here. If we take minus 7 pi over 4, that's going around clockwise, 7 pi over 4 this direction, and 3 square root 2. That's by subtracting 2 pi from the original angle that we had to get this angle in the same positive r. So those are some of the points, some of the ordered pairs we can do to find polar coordinates for this point 3, 3. Well, now the next topic then is we also want to be able to convert equations. Some equations, like in orbital mechanics, the equations are very conveniently done in polar coordinates because, after all, gravity is a central force. It's the same regardless of which direction you're pointing. It's the same strength. It depends on only how far away you are from the sun or something, if the sun is the gravitational force. The result is that the equations for motion in gravity are convenient in polar coordinates in many cases. And others too. If you look at charged particles, they have a radially symmetric attraction to other charged particles or repulsion from them. And so those are best described in polar coordinates. Here's writing an equation in polar form. By the way, they point out in here that your graphing calculator has a polar mode. If you go to mode, and under the coordinate thing, switch to POL, and you can make polar graphs on your calculator. You might try that. Suppose I want to write x squared plus y squared equals 9 in polar form. You can always just substitute x equals r cosine theta and y equals r sine theta, and this will work out. Let me point out this equation. Suppose I had x squared plus y squared equals 9. I want to write it in polar form. Well, I just replace x with r cosine theta. Because this always works. This is the easy direction, right? Is to replace x with r cosine theta and y with r sine theta. There's no ambiguity of how to pick the angle, right? So, this equation is equivalent to this one. Now, even though this is in polar form, what you want to do is simplify it. Often their trig identities help in that regard. So this is equivalently r squared cosine squared theta. Oops. Y is r sine theta, sorry. And this is r squared sine squared theta equals 9. And now I notice I can factor out an r squared and write this is r squared times cosine squared plus sine squared equals 9. I'm going to write 9 as 3 squared just for convenience here also. Sine squared plus cosine squared is 1 by the Pythagorean identity. This equation is equivalent to r squared equals 3 squared. See how much easier that is in polar coordinates? Why is it? Because maybe you recognize x squared plus y squared equals r squared is a circle of radius r. This was just a circle of radius 3. Of course it's convenient in polar coordinates. It's just, it depends, the circle depends only on r, not what angle you're at, to get all points at a given distance from the origin pole. So this is another equation for it, but moreover, you can actually do this better, simpler. And even simpler, you can just write r equals 3, and that also sweeps out, right? R is the distance from the origin, so this says all points at a distance 3 from the origin. That's a circle of radius 3, right? Or you could have done this one, r equals negative 3. Either one of these equations would solve it. I mean, if you solve this, this has two solutions, r equals 3 or r equals minus 3, but both of them are the same set of points. So usually what we do is we say the circle is r equals 3. And there is the polar equation for this one. Look how much simpler it is. Any circle that you plot in polar coordinates just has the description r equals the fixed radius of the circle. That's how to write an equation for a circle in polar coordinates. Very easy. So that's what they do here. And that's the big hint then is, even though you can always do it this way, I started to say before, what's actually easier is instead of using those conversion equations, you can use either one you want. Remember from the other conversion equations, x squared plus y squared is equal to r squared, so you can immediately jump from here down to r squared equals 9. And then you can put r equals plus or minus 3, and either one of them generates the circle. So when you can, if you see an x squared plus y squared, just to immediately replace it by r squared, save all these intermediate steps is the point of that problem. How about this one? X squared plus y squared equals 6y. How can I write that as a polar equation? They have nice examples here, is why I picked this. Well, we use directly x squared plus y squared equals r squared to avoid having to go through the Pythagorean identity again. We write r squared equals 6y. Now we substitute for what's left because we don't have a convenient thing. Y is equal to r sine theta. We have r squared is 6r sine theta. R squared minus 6r sine theta equals 0. By subtracting it over to one side. And we do that because we notice then we can factor out an r. We've got r times all of this equals 0. And there's, remember, the zero product property. A product is equal to 0 if and only if at least one of the factors of things that are multiplied, is equal to 0. So either r is 0 or r minus 6 theta is equal to 0 in order for their product to be 0. They say we reject r equals 0 as it only represents one point. What they're saying there is that r equals 0 is a solution, but we don't need it because the origin, the pole, is already a solution to this equation. So we can throw out this one, we don't need it, it will already be a solution. If you put theta equals 0, then you'll get r equals 0 out of this one. Any angle with r equals 0 is the origin. So we'll just keep this equation, r equals 6 sine theta, and that's the equation for this object that actually turns out to be a circle. If you were to go back to this equation in rectangular coordinates, subtract 6y from each side, and complete the square, like I believe we did earlier in the semester, you would get the equation x minus 3 squared plus y squared equals 3 squared. You get the circle of radius 3 centered at 0, 3. So by completing the square, you can figure out in rectangular coordinates it's actually a circle, but it actually has a slightly easier equation in polar coordinates, r equals 6 sine theta. This is the kind of curve you'll actually see used in calculus sometimes. How about lines? Can we write a line as a polar equation? Well, it's pretty easy. All you do is replace y with r sine theta, x with r cosine theta. Since I can't apply the other two identities easily. And what do I get? Oops. So you can try these on your own. R sine theta, r cosine theta. And now r factors out, you can write r r times sine theta minus 3 cosine theta equals 2. I'm okay with on the test you writing it in this form, but I did want to point out that actually in applications that you'll see later, typically they like to write r as a function of theta. It's easier to graph that way. Each point you plot, you turn to an angle theta and then you go out a distance r. Turn to a new angle theta, go out a distance r. You can build up a table of r versus theta and plot curves easily if you write r as a function of theta. So let's solve for r out of this. Strange. Should be r equals 2 over sine theta minus 3 cosine theta. Would give you the equation for this one. But like I say, I'm okay with leaving it here. All right. How about this one? Write this one in polar form. Again, if you add the x squared over to this side, then you'll see the Pythagorean identity applies. You get, if you add x squared to this side, you get x squared plus y squared equals 3, becomes r squared equals 3, becomes r equals square root of 3, the circle. So that's that one. Again, just add x squared over and do like we did in the other example. This is a useful topic here. It's not really in your homework set and not quite as important. I'm going to omit this one for now, but we'll just say to graph these things, sometimes it's convenient to convert to rectangular coordinates, and that's the next topic actually, is to convert from polar coordinates to rectangular coordinates. So I'm not so concerned about the graph, but let's see how we can convert it. Suppose I have r equals 2 secant theta. How do I convert an equation like that? There's no secant in those conversion equations. What you do is you make it fit kind of strategy. You try and put it into some form where you can see an r cosine theta or an r sine theta and replace that with x and y. Or if you see a tangent theta, you can replace it with y over x. Or if you see x squared plus y squared, you can replace it with r squared. But what you do to convert from polar to rectangular, it's a little harder. You try and make it so you see those four things that appear in the conversion equations. So I'm going to write 2 secant theta as 2 over cosine theta. I have r equals 2 over cosine theta. Now if I multiply through by cosine theta, I have r cosine theta equals 2, and r cosine theta is my conversion equation. I can replace that with x. This is just the line x equals 2. You do have to be a little careful with these things. There is a possibility of secant theta being undefined at certain things, and we ignore that when we multiply through by cosine theta here. So r equals 2 secant theta is this line x equals 2, but at theta equals pi over 2, let's see, pi over 2, secant is undefined, and fortunately that's the angle in this direction, and also minus pi over 2, that's the angle in this direction, doesn't contain any points on the line, so this is actually just the line. But you do have to go through and check and make sure when you multiply through by cosine theta that you didn't introduce some new solutions. Before cosine theta couldn't be 0, but once you multiply through, this cosine theta can be 0, so you check those angles that would make cosine equal to 0, throw out any points that don't apply. How about this one? R equals 3 over 1 minus 2 cosine theta. I said orbital mechanics are very interesting. This is actually one of the equations that appears in making orbits, this kind of a thing. You'll see it if you take calculus. How can I convert that? Well, let's see. 3 over 1 minus 2 cosine theta equals r. And so I multiply through by r by 1 minus 2 cosine theta. There's an r missing here. You get r times 1 minus 2 cosine theta equals 3. Now you can use the conversion equation that cosine theta equals x over r to eliminate theta. And you've got r minus 2x equals 3. Solve for r, and you got r equals 3 plus 2x. Now, you don't have an equation for r. You could replace it with square root of x squared plus y squared, but that eliminates the possibility that some cases with r negative that satisfy this equation. So you square both sides and get r squared equals this. This has the problem that might introduce new solutions. So you just have to be careful when you're all done. R squared equals this becomes x squared plus y squared equals this squared. Now you got the equation in rectangular coordinates. So to convert this one, you try and again you can replace cosine theta with x over r. You try and get r squared rather than r. So you can replace it with x squared plus y squared. Alright, well that pretty well covers what we want from this section. I want to do one more example here. Suppose I have r equals 2 sine theta, I want to write that in Cartesian form. How could I do that? I could replace sine theta with x over, with y over r from the conversion equations. Sometimes it's more convenient just to multiply through by r and get r squared equals 2r sine theta also. But, there we go. If you multiply through by r, you'll get r squared equals 2r sine theta. R squared is x squared plus y squared, and r sine theta is 2y. So sometimes multiplying through by r gets these things so you can recognize them.